Yeah, you can record. Okay, hello everybody. Good morning. So today we are going to talk about the different topics. First of all, post graph optimization. Then second, we will talk about the visual feature extractions like SIFT, brief, and ORB. Then finally, we go through the ORB-SLAM itself. Of course, ORB-SLAM has too many components that are not coverable in short time, and it takes long, but we will try to cover the basic elements that are needed in order to understand the basic concept. But of course, you also need to study much more to make sure that you understand it well. But of course, we try to clarify the small elements one by one. So first of all, we will start today with mapping. We talk about the mapping with when we don't have any uncertainties. Then we talk about when we have certainty. For now, everything is clear to clarify what's happening. Then, as I mentioned, we talk about the post-graph optimization. We will understand how we can improve the performance of mapping using post-graph optimization. Then we talk about the visual feature extraction, SIFT, brief, and ORB. Then we talk about also bundle adjustment, what is the main concept, and what the role is playing in the ORB-SLAM. We talk about also visibility and covisibility graphs, what they mean, and what are the motivation behind. Then, as I mentioned, we went through ORB-SLAM. But before continuation, do you have any question about previous topics and courses, or any question about anything? Okay, good. So then, fasten your belt. Let's see what's happening. First of all, we said that in Islam we have two general class of algorithms. One class is online Islam, that in online Islam we are doing the filtering, like we've learned extended Kalman filter, unextended Kalman filter, particle filter, that they are mostly for state estimation based on the current measurement and previous belief. So this was mostly our focus, but on the other hand, as I mentioned at the beginning, we have full Islam problem too. In full Islam problem, we want to use full trajectory or full path of the robot that is moved in the environment in order to construct the map. Not only relying on the previous belief to do all calculations and predictions of the map. So, of course, in online Islam, we have more real-time and more lightweight approach and techniques that can be onlinely predicted. But here, we have, for example, techniques like post-graph optimization. That, as you know, optimization techniques are also costly and may take longer depending on the performance that we want. We have greedy techniques to solve it, but still are much more costly. But what's the reason that we go into the post-graph optimization and full Islam? The reason is that we want to don't throw out all the information that we already have. Like robot moves in the environment, we have some poses, why don't use them? The reason is over there. So also this is known as smoothing, that is like a name given that says, okay, how with full Islam we can do the smoothing of the estimation of the robot pose when we are solving Islam problem. So let's start with the mapping without uncertainty. It should be very clear that if we have robot and this robot odometry model is very accurate, or we can call it also as depth reckoning. That depth reckoning means that we counting number of steps. Also is famous in publications. I mean, the name that has been used in research studies and publications, and we say that recognition is equal to odometry. And on the other hand, if you consider our observation model has no error, LiDAR exactly can measure the distances of the any obstacle and landmark that we have. Let's see what is happening. So we have the robot over here, and robot observes. So if this is field of view of the robot, whatever scan it has, if this is the field of view, and these green ones are the observation of the robot that sees the environment. Based on that, we can construct a map, save a map on the 3D point cloud or 2D or whatever we want. Then continue. Robot moves in the environment. We run a trajectory, scan again. So we add new part of the map that robot has seen. But since we consider by default that, if we consider by default that robot trajectory has no error, observation has no error, of course this is easy. Then we continue, robot moves a little bit more. We have like amount of translational rotation of the robot based on the odometry and observation, then we construct it. We continue, robot rotates, sees that green part, then we add it in the map. Robot moves, robot moves, robot moves, and we continuously do that. So this is very easy, no problem at all. But the point is now that of course, that's very ideal. We have the problem that whole class we were trying to solve that. First of all, we have error in odometry model, and also we have error in different sensor models. We can say LiDAR almost is accurate, but still there are lots of noise inside, and we need to do some filtering, and of course, is not 100% accurate. Now let's see if we run the same scenario, what is happening, to understand whole idea. So robot again is here and sees the environment as observation. Robot moves this time, and after robot moves, the new data that is coming based on the error of the model that we have, estimation will be wrong. Robot, our estimation, if we don't want to apply any algorithm, thinks that this wall over here now it is there, or this obstacle edge over here that robot was measuring is now here and there. And if we construct without doing any improvement or anything, we have like observation like this. Then the map construction will be like this. If we continue, what happens? Again, we have more error on the odometry, and new line becomes something like that. If we continue more, then you see that like this time, this wall estimation comes like that. If we continue, if we continue, if we continue, and if we continue. So what you can see really, if you want to implement it, it looks like something like this. So this is the problem that we are trying to solve. But now today we want to more focus on the visual part of the how we can deal with this problem. So far we basically try to focus on the algorithms that are, first of all, online. Second of all, although we extracting landmarks and features, by default we said that we know the features, we know the for example correspondences. But today we want to, first of all, more focus how really from visual information we can extract first, create landmarks, how we can match the features together as first step, then bring it to the another like big algorithm. So we say one of the ways that we can do and represent the SLAM problem is use of the graphs. So we want to say, instead of, okay, for example, occupancy grid mapping and having all the estimation based on the previous predicted belief, the belief and predicted belief, what we can do. We can say, okay, let's consider each one of the nodes of a graph corresponds to the pose of the robot. On the other hand, the edges of between nodes is the relationship or the constraints between the robot movement, so that we can say, okay, my robot control command is I'm running, and I can connect two nodes together based on that constraints. So that after extracting these nodes and edges, we can save combination of those, and we can construct the pose graph. What does it look like? So let's have a look at the same example to see what is happening. We say the robot is here, again the observation. So I have a point here that this wall that you can see here, that can be point cloud, that can be laser scanner. We scan, then we have points over there. But here I didn't represent the noise. So after moving the robot, now in pose graph estimation, what I want to do, I want to create nodes. So we can call these guys over here nodes, and we can create edge between those. Of course, maybe robot from here to there move like this path. Robot can create any other trajectory. But in pose graph optimization, for simplification, we want to create a relationship between current pose and the next pose, and make a graph based on that. So as I explained, we have node, we have link or constraints, and another node over here. So now the idea is, if you look at the animation on the slides, both rotation and translation can be applied to improve the error that we've had there. How? So let's say this is the distance that the robot has been moved, and now I can use those information based on the amount of movement and the amount of error that I estimate my movement has. Then I can move whole to the better estimation, to have better estimation based on this amount of movement on the link. So now let's say robot again runs the same trajectory of previous slides, and if we want to construct the pose graph in during time, so robot was here, rotates, moves there, rotates, moves there. So this is like the trajectory, and I'm creating just links between those nodes. Observation is of course the same, so I'm just showing the same observation without improvement yet. We are only just creating creating the pose graph. Then we continue, robot is there. Then we continue, robot is there. Now the point is, after arriving here, robot moves over there and see this frame. But this frame, if you have a look, this frame is supposed to be this one over here, the green one. Better to show it in this side. When we are here, they scan the information that comes from environment, supposed to be similar one than this one. That we know it as loop closing, and we need to detect it. In order to detect it, we will discuss a little bit more. But if we consider that we can detect it, now what can happen? So look at our pose graph and look at the robot trajectory, real trajectory. This is circular, but there we have error. So what we can do, now we can say, okay, using pose graph optimization, we can say that, okay, this position that robot is supposed to be this one. Now I can move this point to there, and with chain rule or optimization techniques that I will mention some, we can then adjust all of these, connect it like it's a chain. I can connect it together, then whole will be reshaped together. So how that's happening, you can see that, okay, we detected the lock closing, we shifted that one. After shifting that one, we can adjust it by any optimization technique that we know, then we can form the post-graph optimization. This technique is very useful, one of the elements of the ORB-SLAM, one of the most advanced technique of the SLAM. That so far we have, of course, we have improvements during time, but this is one of the elements that we have there. We have some notes here that I stated for you that we keep the relative distance and adjusting the loop closing problem, and we can, in the optimization parts, we can use different techniques. For example, least square error minimization can help us to do that, and here I stated, I put it some source or original paper that you can study to see details of how you can implement it. During this chapter, I will have a lot of these. If you want to see more details of the calculation, proof, or something, you can refer to the original paper and see what is happening in details much more. So what are the advantages? Now you can say yourself. We say we have better robot pose estimation, of course. Because previously, so far, before this today, what we studied only relying on the previous one. Then we were throwing out, this were becoming belief, and next one, previous belief. But now, we can use whole information that we have from the environment. That's then we say we need to have a path instead of having only one trajectory. And it can result to have better model of the environment in general. So we have a couple of points also here. We say data association is important. What does it mean? It means that, so our robot was here, let's say we close the loop, and if robot moves and moves, again can see some features of the environment, then again we can perform that already have seen, and again, for example, here detects this corner over here that maybe can be detected. Of course, this is not very good example because this part is similar to that part if the observation is like this and here like this. But anyway, let's say it is detectable. So we can rerun the loop closing problem to again adjust the whole trajectory that we have. But the point is, so you can see in the animation here that we have, so let's say we improve it much more. But the challenge is here that, okay, if we in the post graph optimization, if the robot, instead of detecting this feature over here, was thinking that observation is from this feature, what would happen? If we wanted to reshape the link, then we would destroy it almost, because the whole graph will be trying to shift from here to, for example, here instead of here. Then we are kind of reforming whole and destroying whole. Because of that, we need to be very careful with post-graph optimization, to have many samples and try to have outlier. Try to detect many and only pick those ones that have high confidentiality, that they are correctly the ones that we want. So data association is important. Very important for post-graph optimization. It's not like predicted belief, you do just one wrong estimation, then in future with seeing the features it can be quickly recovered to what is the correct position. Here we can destroy. So I stated some points here that bad association is very bad and we need to discard it by feature outlier detection and remove the bad candidates from what we have in post-graph optimization. So is it clear so far? Any question? Okay. So what about the optimization part? Optimization part can be done with any online or offline technique. For example, some of the optimization we have seen ICP, we've seen like five, six different techniques of the iterative close point, so that we saw how, for example, in simplest form, calculate the center of mass, rotate and align them. On the other hand, we usually use least square error of the minimization technique, so that what is the motivation? Motivation is that if we want to find the error of the, for example, prediction or the alignment, we just find the distance of the residuals of this line with each individual one, and then sum them up to have the general error of our pose optimization. So least square error minimization is a technique due to that least square error that we can use the mathematical regression analyzers and determine the best fit and detect try different methods, like ICP also was using in some parts, that how to minimize the error over there. It should be clear. Now the question is, okay, so far we know that pose graph optimization idea. What to do after doing the pose graph optimization? How we can map it? So the answer is, we can use different techniques. One of the famous ones that also has been used in ORB-SLAM is binary occupancy grid mapping. So that how does it look like? We already have studied in details how we can map it, how we can update the beliefs of each individual grid cell. So we can say, same example that we have, robot moved in the environment, and these are the values that robot observed. So what we need to do, based on the how many times we see, and based on the observation error that we have, we also can use the base filter in order to represent the map that we have. For example, here, if we have like high centrality of the observation and multiple times of observing that this cell is occupied, that cell is occupied, with the updating the base filter, we've seen that how we can increase the certainty here. And for example, here you can see that robot many times has seen error, and this is like grayish with different color that says our map is less certain that this is wall here, or one of these are representing wall here. So any question? So the thing is, like, the obstacle that we had there, just here we have the edges, not the obstacle behind, because we are not observing what it is over there. So pose graph optimization, then mapping, and after mapping, I have some points here. Here in pose graph optimization, we're using full SLAM, that not only belief and predicted beliefs, that we can have also much more accurate one. A practical and exact implementation instance you can see here, that we have a corridor that the robot has moved in the real environment and constructed the map. But this constructed map, you can see we almost don't understand anything. Everything is like, this is from MIT, the code. Then after optimization, if we apply the optimization and construct the map with the occupancy grid mapping, you can see that pose graph optimization helped us to reconstruct the map pretty nicely, and create probability that these white points are free points, black points are filled, and the gray scales are like 50-50, that we don't know the observation what it is there. So if you also want to see the details of how this is happening and how they conducted the experiment, you can look at this paper over here, that's how it is working. Any question so far? Okay. Now we want to talk about a little bit more and open the visual feature extraction. We want to see, when we are talking about the observation from environment, how exactly this is happening that we can extract features. Of course, based on the different observation sensor models and between different sensors, that can be varied. But here we want to try focus on only camera because it's much more, first of all, accessible for us, cheap, and also is like more understandable. Because we already talked about like LiDAR scanner kind of mapping with constructing the point clouds and running ICP to construct them. So to understand this, we will see different algorithms. These algorithms are very common and famous in machine vision, robot vision techniques. We have algorithms like SIFT, SURF, BRIEF, and ORB. Why we don't directly go to the ORB? Because to understand the ORB, we have to come from here. We have to understand what is happening here, almost what is happening here, then we can talk about the ORB feature extraction. But finally, after understanding this, I will show that there are, of course, many libraries and implementation examples that already did it for you. You just need to call and it will run for you. But we want to see really what is happening, not just using what is existing. We have to understand what is happening in order to extract the features. And if we want to do research, of course, we need to improve these by knowing what is happening in, on the background. So these techniques have two steps. These two steps or two elements, first of all, is extracting the key points. So that key points are extracting the location of the distinct local feature in the environment. After extracting the key point, so we kind of need to describe it. So this is the key point. Okay, I found it out that this corner over here is the feature that my camera sees, and that's. But how to describe it? We need to propose techniques that describe the extracted key points. And why we need to describe it, do you think? Yeah, to match in the next, to use it in the next steps. Like, okay, I extract the feature from here. Then robot is moving. So just extracting the feature is useless. Later, I need to kind of describe that feature so that if I see it in future frames, I can say, okay, this guy was the same guy that I'm seeing. The motivation, the idea of descriptors is to describing the features of the key point. It's like I'm seeing you. Of course, I see that like you wear red jacket and your face features, and the other, everybody, I extract them, and I have some information as descriptors in my mind, and same thing, something similar is happening here, but in form of vectors, not learning technique usually. But of course, it can be learning technique. You can, when I'm diving into, you can think about, okay, how we can do that in much more advanced techniques, how I can propose new technique in order to do the same thing with the algorithms that I know. So what's the idea of first stage? We can say finding local distinguishable points as features. If I find feature from table surface over here, it's almost useless, because if I move here, it's almost same, right? So if I'm looking at this wall, if I try to extract feature from here, this plane is useless, because if I go somewhere else, it will be pretty similar. So the motivation is kind of find the distinguishable points. Like I'm looking here, if this is my view, the most important is like that feature, these corner features. So the idea is try to find distinguishable features. so that in new frames or different views, I can find the correspondences. Here you can see that we have two image frames that we extracted some features over here. We will discuss soon how this is happening and what are these ones. But you can see that from sky, we don't want to extract any feature. And even if we extract features from clouds, they're going to move and go away and destroy our information. But the technique that we have, you see that mostly extracted features from the parts that are more important. And here you can see that also the features that we extracted are much more reliable. And as a human, if you can see, there is not any element from sky. So in order to understand what is happening, we need to dive in the first algorithm of the feature extraction, SIFT. It is scale invariant feature transformation. That his name is SIFT, and let's see what is happening. First of all, we don't have only these 3 or 4 algorithms. We have many different algorithms that can give us features of each frame of the picture. For example, we have Harris and many others that they are not usually robust in order to extract the features, or if they are robust in order to extract the features, they have some problems. Some of them are not invariant for the rotation or scale. Like, for example, this is the feature that we extracted, the same thing. If it becomes bigger, then our technique, just like with for example, Harris, just takes this part, this part, this part, this part. But this should be seen as general view, not small elements anymore, in order to match. It's like you detect a feature, your robot moves to the closer, then same object will be bigger, and we cannot detect. So that we say SIFT is rotation, translation, and scale invariant. You can see it's in name too. So scale invariant feature transform. SI is standing for scale invariant. So and this makes it very suitable for landmark detection in the SLAM problem that we have. That usually it has like the technique includes the ways that removes the illumination of the distance that we have, and of course the scale. How it is working, we have some main steps. First of all, as we stated, that all of the techniques that we are going to talk have it, extracting the key points. Second, computing the descriptor for each one of the key points. Let's dive in first step. What is happening? We are detecting corners, that is including the edges of the frame. So we get the frame of the picture of the environment, then we want to calculate the edges, extract the edges. So how we can do that? We can use gradient. What is the gradient? Gradient is big change in the brightness in the environment. So when the change in the brightness is happening, if you look at, for example, the corner of the door over here, where the visual information, this is like changing, the color is changing dramatically there. So that can be the motivation to extract the features. Or here, for example, here and here. So wherever that is happening, we can say, okay, we want to extract the features. So what we're doing in practice, we are searching for intensity change. So how does it look like? Let's have a look. If we talk about a small discrete part of a frame of image, we can say, okay, we can have a part like this. Like this is the part of like a frame, small cube, that the color inside is looking like this. Another cube of instance of image frame that we have looking like this. This part is more darker, this part is white. Another one we can like this. Upper part is darker, downer part is whiter. Another one is like majority part is dark. So what we are looking here, we are looking for locally distinct information that that also we can say mathematically they have larger eigenvalues. So that we already discussed what is the eigenvalues. So based on that, we can say, okay, let's average the information that we have, intensity that we have inside. So if we get the average of the intensity and try to draw some arrows to represent what is it looking like, here the arrow is like in the same size because the intensity distributed evenly inside the part that we have over there. But here you can see arrows more tending toward the lighter part. That shows us information of this part that we have. And here you can see the arrow to the down is higher because the lighter part is in downside. And here you can see something similar. Of course, here we have much more because only the light part is in the corner, much more representing that, okay, it should be in the corner of that that part of the image. Now you can imagine yourself, without even moving further more, if we have a frame and if we grid it and if we can calculate intensity for each one of these small parts without doing anything, then we are converting RGB image to some information. That information are like for each one of the cubes we can have two values. Kind of re-encode all information of RGB too many to small grid cell some values that represent something meaningful for us. Okay, so far. But of course this is not the thing, but generally what is happening. So we have a couple of steps. Let's see how SIFT algorithm is working. First of all, we need to after doing that step, we need to apply different levels of the smoothing or blurring. We can apply different levels of Gaussian on the image frame. So you have pure image frame that is completely normal. Then you can apply different Gaussian models on that to make it more blurrish. So after doing this, we can, the idea is subtract two of these levels that are like, if you increase the level of the blurrish, you can subtract 2, 2, subtract 2, 2, subtract 2, 2, and continue in the second layer. So if you subtract these two, subtract these two, subtract these two, so you will have higher another layer that shows the differences of the Gaussian. If you want to understand it, we can say, okay, if we have this blur image, and if we subtract it with another level of blur image, we are extracting, we are getting the information like this over here. That this is one of the elements of the SIFT that we need to apply, we need to do in order to first of all extract the information that we have from image. Second part is applying different scales of the image, because we said SIFT is scale invariant. It means that when the camera is moving much more closer to the obstacle or object that we have, it can detect this scale. How that is happening, the idea is looking like this over here, the step that we have after applying the different level of the Gaussian, subtracting them in order to get the points. Now we can say and do the same job on different scales. Resize the image, make it smaller, and do the same thing on the frame. So that we kind of saying, okay, if I'm seeing this in a frame, then I'm considering, okay, make it smaller, 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 so that when I'm going farther, then I know what it should look like. So that gives us the looking at visual this one. So we applying the same Gaussian at this size and make it smaller and applying the same Gaussian, then doing the subtraction in different levels and layers. So after that, for each one of the key points or corners, we need to find the best and the maximum value and looking like how we can do that. So after doing this scale and after applying the Gaussian and doing the scaling on different levels, what we can do, we can now find the extrema points. Extrema point says, okay, in different layers of the results of the subtraction that comes from there, now we can find the extrema points. That is kind of saying the computing the corners that which one of the edges have maximum value in comparison. If we compare these 2 points like corresponding points, we say which one is more reliable, which one has higher value as maximum point. Then in different layers of the in different scaling and in different layers, bring the more important information out, so that we have then the features that looking like this. Doing different Gaussian, subtracting, then after subtracting the finding extrema points, which one are more reliable in different views, then we can extract features of image as looking like these circular points over. So now let's say we have these points. What is the next step? Next step saying, okay, how can I say what this picture, this point over here is looking like? What is this one looking like? In order to do that, of course, I want to match the information of the left side, for example, with another image that is coming from frame that is rotated or from different angles or from different distance. So that in frame A, I'm detecting these features. In frame B, I'm detecting these features that can be different. Now I want to say, okay, which is this feature? Which one is this feature in that frame? Which one is this feature in that frame? How can I do that? By describing each one independently. And that description looks like something like a vector like this that we want to extract. We will see how to extract. Okay. What is it SIFT doing? We say SIFT saves the location of the pixel of the feature that we extracted, gets the scale information, gets the orientation and descriptors itself into as information inside. What does it mean? Location is the pixel location of the keyframe, where it is. For example, when your camera is seeing some feature upside, more likely wherever you go, it should be upside. That's why position is important. Something is on the ground, some feature is not going to fly after 1 hour, right? It's usually mostly is downside. Because of that, location is important feature. The scale of the key point that we can got from that we can say how the differences between the frames has been changed. So we will discuss it how that's happening. Is like when we are extracting different layers and rescaling it. So when we are subtracting, actually also we saying, okay, this feature and this feature are getting smaller or bigger. So with getting differences between the rescaled one, we can get the information of the scale part and put it over there. Then the orientation the orientation of each key point. In next slide, I'm going to show how that's happening. The orientation is like, okay, we need to calculate this point over here. Of course, it's circular point. We don't have orientation there. We will see how we can how we can extract some information in order to give orientation to save it in the frame. Next slide, we will see. And the descriptor, that is 128 dimensional floating point numbers that stores some local surrounding relations of this point. Not only those information like the location, scale, how big the scale is, and the orientation, we also want to describe it with some features. How that is looking like, let's have a look here. Let's say our SIFT algorithm detected these features. Some of these features are like small corners. Some of these features are bigger, a little bit bigger size. That can be based on the applying Gaussian and finding maximum extrema finding. We say per each one of the features, let's choose one of the features and make a grid around surrounding that feature. The size can be depending on the parameters that we are detecting. So after we having this, for example, extracted feature from SIFT, we put a grid around it. And how that is looking like, it is looking like this one. We say, okay, we can break it into 4 times 4 cubes, 1, 2, 3, 4, and each one again 4 times 4 cubes. That is representing this circle here in form of cube. Then we can compute the gradient. And if we compute the gradient based on this, what we want to do, we want to say, okay, this part over here, this small part region over here, should give me some meaningful information. This part over here should give me some meaningful information. In order to do that, we can, for each one of the parts, we can apply the key point descriptor that says, okay, what is the intensity over here? You can see that like this part is white, this part is darker. Based on that, I can bring it to the n to the 8 different values. That is kind of, instead of in the couple of slides ago, I just showed it with 2 arrows. Here I can show it like with 8 arrows. In SIFT, we have 8 arrows. We can give more accuracy, bring 16 arrows or whatever. Now, what is the idea? Taking the feature that we detected, giving some neighborhood for that feature. Not only that feature, giving some neighborhood that is bigger. Then create intensity, then detect some values based on the arrows, and how we can now present it in the form of the descriptor. We can say, we can apply the histogram of these ones and say, okay, how many of these arrows are existing over there, and say, okay, to the right is this side, like this many, to the upright is this many, just count them, how many of these are over there, and get some values based on those. Just put numbers. So these all values, these all calculations can come to the numerical values. Now you should, okay, the idea should be clear that now I can describe the features. So that this feature over here that I can see is different from this feature. How? Because of its neighbors, its intensity has some unique information that this one has no. So what we do, 4 times 4 times 8 becomes 128 dimension descriptor that we added in the key point frame over there, so that we can use it in order to match the key points frames by in different frames that we are observing. How that can happen? How we can match the features? What do you think? Now, simply we can find the, for example, let me see, we can find the Euclidean distance. We can say, okay, we have one for each one of these. I have descriptor, and for each one of like here I have descriptor, and here I have descriptor for each one of those. Then I can compare it by calculating Euclidean distance among all of those and all of those. Clear? What's the problem then? We have a big problem now there. Problem. What can be the challenge? No idea. Everybody is sleepy. Yeah, this is just beginning. We have today long way to go. This is the easiest part yet. So the problem is Euclidean distance of each one of these descriptor. Let's see, I have this point over here. Now I need to match it with this one. How can I do that? This point should be compared with all of these, right? Now the second one should be compared with all of these. Third one should be compared with all of these. That is big array, and calculating the distance of the arrays. Very expensive to compute. So that's one challenge that we have. We will see how to improve it. The other challenge is similarity in the image that can give us more correspondences, also wrong correspondences, that we say, okay, this guy over here is very similar to maybe I don't know which one maybe can be more. So the tree one, the features from tree can be very similar to other part of tree. That makes it also a little bit challenging over there. So how we can solve that? We can in order to not only the computational complexity but also similarity, in order to deal with it, we can say choose the best matches and create threshold value in order to throw out the outliers, the features that are not very reliable. How you can do that? What do you think? The simplest technique? If you have those arrays, the key descriptors of this. Now if I ask you choose some of them that are more reliable, what you do? The easiest way is like choosing the ones that more value in descriptor, that the differences between the brightness is too high, gradient is too high. When gradient is too high, you can say, okay, for sure this is corner or something. It's not like shadow. Clear? So where can I exemplify this? So the corner of this table is white. I detected that feature, but the corner of this one that is on the with white side, there is a high contrast, is more reliable to detect than this corner over here. If this is black, even for human, the brightness is in highly contrast, you are less chance to hit it because you obviously can see that is black, that is white. But if they are both totally white, even human is hard to detect it. You may hit it or something, you then don't see it. So although you can detect it. So that's one technique of outlier detection. So as in advance, the biggest challenge I explained to you, the SIFT is very expensive to compute. That I stated over here for you. So in order to now deal with this challenge, we are moving to the next algorithm, pre-algorithm almost, that is binary descriptor. We want to see first of all what is the binary descriptor, then how we can bring it into the game. So the idea is selecting a set of pixels around the key points of each frame, then computing intensity using the single pattern to perform it. After doing that, we are concatenating the comparison of the results all together with some simple rules with binary descriptor. So we want to now say, okay, that big key features descriptors that we extracted, the array, is very nice, but it is expensive to calculate. It is expensive to calculate the Euclidean distance. Now, how we can bring it into the binary descriptor is like 3 steps and 1 rule. The rule can be defined by ourselves, is like one if else. Let's have a look in the next slide. What is it looking like? Let's say this is the same area that we chosen, and this represents pixels and the intensity of the pixels. We can say, okay, let's have some comparison between these pixels that can be random, that can be on some patterns that we will see. Then apply some rules. So I'm saying the pixel number 1 and 5, 6 and 4, 8 and 6, 3 and 7. I'm creating a rule. What does it mean? I want to compare pixel number 1 and 5, number 6 and 4, 8 and 6 and 3 and 7. So if I apply this rule, if the intensity of P1, pixel 1, that is this one, and pixel 2, that is second one, what can I do? Like if this is smaller than that, put 0, otherwise put 1 over there, so that we can compare it. If pixel 1 is smaller than, the intensity is smaller than pixel 5, is it? No, 0. 6, is it smaller than 4? 6, 4. Oh, it is not clear here, but in this monitor, low quality, but it is, so then it is 1. Believe me. So then 8 and 6, 8 and 6, 1, yes, it is intensity. Then with 3 and 7, it is not. 3 is not great, it's smaller or more brighter than the 7, then it's 0. So what I've done now, beautifully, with binary descriptor, instead of calculating that descriptor that we had as like big array of the information, now we put 0, 1, 0, 1, 0, 1s in order to describe the neighborhoods of each one of the key points that I extracted. So we had the image. We have something here, like some for example, building with some trees. Then whatever that we have. Then we extracted some features. Then we say, okay, for each one, I'm creating neighborhoods. Then here, I created some values, but instead, I can put them as 0, 1, 0, 1, 0, 1s with binary descriptor. Clear? What is the main advantages? It's clear that less computational complexity, compact descriptor to store the data, it is smaller, requires less memory, and fast to compute the differences between two descriptors, because this binary value is like very easy to compare with in comparison to that one. Now, based on that idea, so why we understand binary descriptor? Because we want to use it in brief. That brief is kind of tries to improve the SIFT technique, and it's like binary robust independent element features. It's like standing for binary robust independent element features, and how that is looking like. It is using 256 pairs of descriptors that is based on the binary descriptor. What does it mean? It gives us some patterns of any region, that these patterns are using the same binary descriptor idea in order to say, okay, each one of these lines, this pixel should be compared with this pixel if you have uniform distribution of the binary descriptors. This one should be compared with this one. So we have a pattern to do that. Another pattern is Gaussian pattern. You see the center is more dense, the corners is less dense. We have another one is like this one. That is like discrete Gaussian. That is less dense with less features. So we have something like discrete location one. That a little bit we have also pattern over there. We have polar. That in polar, like everything comes from center or crossing from center to compare the pixel points. So what does it mean? It means that we want to use this idea of the binary descriptor and use some predefined patterns in order to do that. So you see that the idea is very simple and the algorithm is very famous. If you go study the paper, it's simple, but too many citations. That this guy, I think this is come from original paper presentation, that he did this experiment and with these patterns for first time, and you can see that the feature detections are working, but the problem is that here it is not working very well with the rotation. So it's not very clear in the image frame, but with the experiments that have been done, I also will show the comparison after finishing the part. We will show that it is not a very rotation robust in the rotation part, but it still can work pretty fine. So you can see the original paper has been proposed in 2011, just giving this idea, combining with binary description, and it is still one of the good algorithms for feature detection from frames. Any question? Okay. So now we want to talk about ORB feature detection. The ORB stands for oriented fast rotated brief, so that we are going to take the brief technique and kind of bring a technique in order to solve the rotation problem. Just we have simple idea to merge it to the brief in order to improve it. So we had the SIFT, binary descriptor, brief. Now we have ORB that tries to improve the latest algorithm. So the idea, of course, it is covering the shortcoming, and ORB performs as well as the SIFT technique. It is as good as SIFT. Why as good as SIFT? Because SIFT was proposing a big vector of descriptors, and it should be the most accurate one, because when we are doing this, we are losing data actually. But in comparison, we will discuss it. So although it is performing as well as SIFT, but also in feature detection task is better than SIFT, and it is faster. So we said ORB-SLAM builds the key point detectors as similar as brief, and let's have a look what is happening. So here you can see two frames of pictures, this one and this one, same image that we have our camera detected from the information. So what is happening? The ORB-SLAM is considering the rotation for whole image. So the idea is kind of saying, okay, I have this frame, and later or during time this frame is coming. If something is rotated in the frame, is not the pixel solely. If the environment, if I'm like looking at the environment from here and I'm coming here, actually it is rotating the frame. And the idea is, okay, if from there and here we have frames of the environment, if you want to rotate something, adjust something, whole should be rotated together. Because maybe a guy is doing that in the middle, but whole scene is not doing that. Whole scene should be rotated all together. So the idea is simple, but very strong and robust, and works perfectly fine. What is happening? How you can guess it? What we can do here? So we don't have the picture. So we already performed the feature extraction part. Then after feature extraction part, we have some points and descriptors. What we need to do, the idea is calculating the center of mass of these detected points. And based on that center of mass of the detected points, that can be calculated with simple equation over there, based on the intensity and the pixels that we have. So, and then replacing with it as like 0 and 1, making as binary descriptor. Then after that, actually here we can put the moment. That is, moment is the differences between intensity. Using that moment, we can calculate the center of mass. That this calculation is here we have the mass of the image block with M00. Then these two, M10 and M01, is the centroid of the image block. Then after doing this simple calculation, we can get the orientation, but by getting the arctangent, we can have the theta and amount of theta, and the place of center of mass can give us the rotation that we want in order to when we are calculating the first frame and second frame, the points all will be based on that intensity, and calculation of the intensity of the center of mass is kind of finding this, and what is the intensity here, based on that rotate it first, then we start to match based on how likely it should be rotated to bring intensity more closer to this one of the distribution of the points. When after you do that, then we start to match it. Of course, we may have still error, but rotation makes more sense to match before doing anything else. So how that is working, if you want to see more details of how this equation comes, how more in details, I'm not going to prove or show more details, but that's like also almost all of the scenario, nothing very complex. You can have a look at the original paper presentation of the ORB feature detections. So what they've done, they've taken the previous technique, add calculation of center of mass rotation, and compare, improve it, and again, very famous publication that is working also nowadays in very advanced techniques. I represented some example code here. You just can copy paste it into your computer, load the image, put in directory test.jpg, then you can extract the ORB features just with few lines of code, finding the key points of the ORB.detect image and some input parameters. That's it. All the efforts can be done in one line now. Okay, question? here we have some comparison that you can see. The comparison of the SIFT, SURF, and ORB. That here, first of all, first table in this part shows the time comparison. What we've done with the techniques that we have, the ORB-SLAM has the less time consumption. It is the fastest one because it uses the binary descriptors. So the time is very important for us. But on the other hand, if you look at the technique itself, SIFT performance match rate is higher. Why? Because it uses the descriptor in form of vectors. Because it's like it saves more features. But that's more than 10 times slower in terms to computing. But the performance, although 10% is higher, but is almost acceptable. Just 10%, we are losing 10% of the accuracy of the match rate, but on the other hand, we're gaining 10 times faster algorithm. That's the first point. So you may say, okay, I don't have any problem in computational power, then I need very accurate one, then I want to use this one. Can I use it? I say still you should consider one more parameter, and that is this one, the rotation. We said that the ORB-SLAM works pretty fine in rotation part, and you can see that if you compare it with directly with SIFT, like both in 0-degree rotation, here the performance was like over 100, but after rotating, for example, 250 degrees, the ORB-SLAM works better. Like this is 93, this is 97. After 80-degree rotation, works better. After the other ones also are also close. I think here, if you compare with this one, I've forgotten to. I didn't mark it because this is not a little bit worse than another algorithm SURF that is also pretty similar. But SIFT is almost close. But if you want to conclude, of course, ORB is more robust in if the frames are rotating too much. On the other hand, faster. Any question? Yeah.
So if I want to match some image where, like in your first example, where the guy who facing the image, like SURF and SIFT will be better than ORB or not?
No, in rotation, no.
Because
in matching it works better. In matching it works better, although this is like very close. But when you're rotating, like you rotate 100 degrees, then that's worse.
Yeah, but the problem is you're not, like in this example, it's really easy because you're rotating the image.
Yeah.
But in the first stuff where the guy is holding,
let me go there.
before.
Yeah.
This one. So now there is something rotating inside the image. So the idea with the center of mass is not good anymore, right?
If you are missing whole object from or partially the object from the frame that we have, yeah, you're right, it's totally different. But we say, okay, we are performing on the keyframe of the video stream, so that the differences of that, if you can calculate higher frame rate, then you will have higher accuracy, because we are not jumping, like going too much, then compare it. Just differences between two frames continuous, then that's the key point. And even if you ORB-SLAM, if you can calculate 60 frames per second, that's the output is higher accurate than like 10 frames per second, because of this ORB feature extraction and feature matching. Because this feature matching, now you can consider, if I have these features and the next features, I've learned pose graph optimization, and those features are creating the nodes and links of the pose for me. I'm connecting those together. When video stream is like I'm detecting the features, moving, new features comes and new frames, and I'm creating pose of the pose graph of the optimization based on that. And that's like how accurate I can, higher resolution I can get. My pose graph optimization technique will have more nodes and will be more accurate during time. It's like, I think it's very clear, but let me also visualize it here. So you have, so instead of having like robot is moving with these big steps of seeing the environment with field of view, FOV that it has, then you have more instead, of course. Then you have more robot poses, and how much more, of course, better, and you don't have that problem that this chair was here, suddenly is not here anymore. No, you still can see it, and new one is coming, then this one, that one, new information is coming and generating flow for me. Okay, I think we can have like 5 minutes break, then continue to the next topic. Did you start? Okay. So let's continue. For now, what we've learned, we've discussed about the visual SLAM, feature extraction for visual SLAM. We've seen pose graph optimization, and we've seen the feature extraction, different techniques. So that now we have useful information from keyframes. Our camera is seeing the environment, and we know almost how to extract the features and how they are working. And based on those features, we discussed some important points that we should like have the outlier extraction, and like the rotation already, if you are using ORB-SLAM, already has been done for us, and tries to decrease the error of the detection of the features from environment, then bring it to the form of having kind of useful key points on the frame for us. But there are a couple of other points to discuss also. First of all, we are talking about the camera, and the camera and visual odometry and visually understanding the motion in the environment is a little bit challenging, and another challenge will be introduced. What is that? Is that you don't know where the camera is, right? We're talking about the robot. When we were talking about the robot, if we use another sensors, odometry, motion commands, a model, then we know those information. But if we don't have it, then what? Can we do something? Then what are the challenges that we have over there? You have a camera, webcam in your hand, and you're walking, and you're trying to solve the SLAM problem. Is it possible to do that? ORB-SLAM motivation is kind of saying yes to also, without using any sensor, any IMU sensor, any motion model to be able to do that. But if you want to answer that, how we can do that, we have another challenge. And what is that challenge? Is bundle adjustment. So what's the bundle adjustment? We say, okay, if you have the camera over here, this camera sees some features. That features in 3D, we can say X, Y, Z of each one of the features. We can detect it. But not only the camera, each one of the features position is important now, the camera position is also important. That we can say the camera pose plus the orientations, 3 degree there too, 3 degree in XYZ, and 3 degree of freedom that it has, rule pitch yaw, for example. Then we have also, we need to add 6 degree of freedom, more problem for the point that we have. So here in this figure, you can see the object, and we have observation on the environment. Then if we have the camera that is moving from different angles from field of view to see the same object, then we need to also kind of estimate where the camera is and where the pose of, not only the pose but also rule pitch yaw and all the orientation to detect the object in order to solve the SLAM problem. Actually, what we are doing, instead of robot, we are talking about the camera location anymore in visual feature extraction. We are not talking about where the robot is. We are talking about where the camera is. If we find where the camera is, actually we find where the robot is too. Correct? Right? Clear? So with knowing this, we say that bundle adjustment is the component of real-time camera tracking system. And it is a state estimation technique for estimating joint of these elements. First of all, 3D coordinates of each point. Second, 6 degree of freedoms of the camera position orientation, that known as extrinsics of the camera. So what we want to do actually, as I explained to you, we want to track and say, okay, we have the pose graph optimization based on the pose of the camera frame that looks at the environment. And what we want to do finally, we want to minimize the error of the projection of each one of the camera, not each one of the one camera that is moving. But of course it can be multiple cameras too. We can consider also there are multiple, but for now, for SLAM problem, we can consider, depending on application, this bundle adjustment can state for multiple camera from multiple views that is looking at the same object, but here we are talking about the SLAM and tracking the camera itself. So it can be, of course, a complete optimization problem in 3D because the parameters that is visible and for example, all features that are visible, in order to extract that 6 degree of freedom of the camera is almost very complex problem. So what we do usually, we use it as least the final step of the feature-based 3D construction of the algorithm is in bundle adjustment, and we say the applications are of the bundle adjustment is robotics, visual SLAM, and computer vision. In these fields, we are using bundle adjustment a lot, and the challenge is minimization of the error of the least square error. Again, in 3D, not only for the points, but also for camera 6 BOF, we want to again minimize the least square error and estimate the data association. Also, that is the hardest part because if the data association is only referring to the finding which point is which point to localize the point, that we have 3 parameters. If you have 6 more, what does it mean? It means that we need to, so we see this, for example, this object from this view. Now, not only I need to find X, Y, Z, but also I need to detect the angle of field of view of my camera that is looking there. That is looking from here, or like this, or rotated like this. And the position of the camera, the pose of the camera, let me say position of the camera is easier, but adding the orientation is much harder, because we need to detect the orientation. So also we say we usually have sparse data from different observations, that this sparse data, of course, as your friend mentions, you may lose some of the data in different keyframes. The same orb features are not extracted, and this can also make it harder. So what we usually do, we want to just formalize it, but let's have a look. We say consider environment with 3D points of the XJs and set of cameras, or the camera that is moving during time in the environment as a camera eye at different times after movement. It is common to formalize it with talking about multiple cameras, but as I said to you here, we talk about same camera that is moving during time. So we can say xij is as coordinate of the j's point screened by the ICE camera. So ICE camera, it means that during time the camera is moving in the environment, and xij represents the same point that is moving on the screen. Therefore, what we can state, we can say the given set of image coordinates that we have as xij is solving, we need to solve to find the camera matrices of the CI and create a matrix where the camera is moving in that 3D coordinates. So that we can say, okay, Ci of the xj is equal to xij, so that we can simplify a problem from the camera and the position to find the both together in the form of big matrix over there. So of course, noise also can destroy this a lot. Data association can destroy it, can make more problem on there. Losing some data can make problem, and the estimation of the, when we are talking about the camera, and estimation of the where the landmark or feature is also can be very challenging. So what we want to do, apply the maximum likelihood or ML solution, assuming that the measurement of the noise that we have is Gaussian. So in simplest form, as you know, we were talking about the SLAM problems, error as Gaussian. And if you consider the same Gaussian error on the observation model that we have here and the observation of the environment that we have, we can say for every view, we want to minimize image distance between the reprojected point and detected one by this equation over here. So that minimum of the distance of the this term over here, Cij x, that is prediction here, as you know that when we have had, these are the prediction ones, and this is the represented by the observation over there that that we want to minimize. So we say, okay, by considering this equation over here that we want to minimize, we are involving adjusting the rays between each camera center and the set of the points that we have. What is the rays between camera and set of the points that we have? We can say, okay, the points that we have, if you can calculate the ray, like a line from here to the points, and if the camera moves, if I can calculate the ray, the straight line to the moves to those points and draw kind of straight lines. So based on that straight line, I can estimate the position and even the orientation of the camera based on that ray. So we can say, besides equivalently between each 3D points of cloud, we can consider that we are solving the problem of finding center of the camera field of view into the ray to the each point. So whole this procedure, solving this procedure optimization problem, we call it as bundle adjustment. How exactly in detail we can solve it? There are multiple different techniques that for now, because if I want to enter to that exactly, will take time. But the objective is to minimize it in order to do that, and we call it as bundle adjustment to see later when we are talking about ORB-SLAM what does it mean. For example, ORB-SLAM proposed a technique to solve this problem. In other technique, other algorithms, we see another optimization problem or maybe heuristic technique to solve it. But for now, you just need to know, most importantly, what's the bundle adjustment and what is the motivation behind. Okay, clear? We didn't talk about solution because it is depending on the application, there can be multiple solutions. But we know bundle adjustment, finding the camera pose, and the object and tracking. On the other hand, as I told you, there are too many elements of the advanced techniques of visual SLAM. One of the other elements that we need to get familiar with to know general concept in order to later understand what is happening is the visibility graph. We need to be able to have visibility graph of the features from environment. And what does it mean? It means that so that we can have like this ABC as feature points from the environment, or we can consider where the camera is observing the environment, so that we can create a visibility graph of how they are connected to each other. Like for example, B connected to C and C connected to A. So this creates the simplest idea of the visibility graph, that if the point B is visible from point A. So if we can construct this visibility graph, it means that there is something in middle that we cannot achieve to see A from B. So this is visibility graph. On the other hand, we have the co-visibility graph. That in co-visibility graph, we have the map empty, that is undirected graph, that there are some nodes and there are some edges. All nodes are representing landmarks and edges representing co-visibility between each landmark. And how does it look like? It looks like this guy over here, that you can see the robot, see some obstacles over there, and you can see the co-visibility graph that we have over there, and like we can add one more feature, then we can construct the co-visibility graph by adding this feature and saying, okay, which one of these features that I'm seeing in the environment are achievable or visible in order in 3D constructed environment to each other. So to understanding what is the application and where we can use it, you should think yourself a little bit now, because this is one element of also the algorithm that we have. So we can say, okay, if we consider the image frame that we are talking about, this image gives us some features that we talk, for example, as ORB-SLAM. And these observations and these points over here that I'm extracting from environment, I can create co-visibility graph and say, okay, is this guy over here from this point is achievable? Is this guy from this feature from this feature is achievable? And I can create the connection between those and connect them. And based on that, I can have bigger frame and bigger picture of environment. So kind of, after applying ORB-SLAM, I'm kind of reconstructing the shape of the environment. with creating that, okay, this feature can be visible from there and connected. This feature can be visible. I'm forming a shape, kind of creating a high-level construction of observation from environment. And this is called co-visibility graph, so that if I can create this can be helpful for me in order to solve a SLAM problem. Why? Because purely talking about ORB features is very nice. We saw that it's working well. But if I can reshape these in form of some bigger construction and form them together, then I can say, okay, we can talk and compare both bigger scale of the features together. The motivation behind is like that in order to construct co-visibility. But of course, each one of these, if you want to formulate, go in detail, takes long. I'm just quickly reviewing what are the general idea to see how that can work. So we say at each image that is processed, set of visual features as LTs, landmarks, we can call them as landmarks. These are detected and represented, and we can represent it like by one of these, like ORB-SIFT, and the co-visibility graph will look like something like this based on the features that we are seeing, and current observation then looks like this guy over here. Then matching this graph by this graph is easier than just comparing identical features together, so that these connections between X over here in the observation is easier to match as a pattern with this visibility, co-visibility graph, instead of just searching, okay, where is this guy, where is that guy, where is that guy, finding the patterns of the features by co-visibility graph. Clear? Just when we are talking about co-visibility graph, consider we don't want to just rely on each individual ORB feature. We want to create some graph between, then another graph, another graph, another graph, and compare graphs between each other to make it more stable and robust, and that's the idea that existing in the ORB. So we can say we update co-visibility map based on the current observation and the vectorial description of the confidence of all of those points together, that we use it for visual localization information in visual odometry or visual SLAM or general problem. Now, with knowing those backgrounds, couple of maybe 4, 5, 6 backgrounds that today we discussed about visual information, we want to enter to the general concept of ORB-SLAM, but still we need to a little bit more, we need to know more that I will explain during the explanations. So first of all, let's have a see general ideas. It is a real-time SLAM algorithm that provide to bundle adjustment with following features. So what is the bundle adjustment now? We want to find the camera poses. I told you I didn't discuss the algorithm because whole ORB-SLAM is trying to solve this bundle adjustment. Find out where the camera location is and where the pose is. Okay? And that's optimization problem. So when you are hearing this algorithm is trying to solve bundle adjustment, then you know that we have camera moving in the environment, we want to find the pose. On the other hand, like in order to do this, in order to solve the bundle adjustment problem, we need to find good features that these good features are kind of subset of selecting some frames that have good features. It means that, okay, not only we want to talk about ORB features, not only the graphs that we discussed, not only all the elements, but also when we have a stream of video that is coming, better to find out which keyframes are more important to extract in order to also increase the performance, increase the runnability Of course, we say how accurate, how much, with much more resolution, we can compute orb features between two frames and compare them together. But also, we say, okay, in some frames, so robot is like, the camera is like stopping, right? Or there is not too much useful information. So better to drop it and have keyframe and extract the keyframes in order to construct better model of the environment. So this is the meaning of the keyframes. Also is not that easy. It's a little bit challenging how to understand what is the differences and how to take the good keyframes. The elements that a bundle adjustment algorithm can be real-time and good, we say selecting the uncertainty redundancy that I explained, a strong network connections of the keyframes of the points that produces the accurate results, including the well-spread keyframes, and of course the features too. If our algorithm is spreading well in order to find better orb features at one part. Second part, better spread of, like, we have 1 second of video frame, all the frames coming from like last moment. Not really good. Although we may say our technique detects that last moment of 1 second, like last 2-3 frames is very important. But we would like to have better spread during the time. If we are talking about 1 second at 30 frames, better to have distribution of the keyframes over there also. Not only just not the important ones. And having plenty of loop closure matches is, of course, the critical point, that if our bundle adjustment can find much more loop closure matches, it will be more accurate in order to optimize the pose graph that we had in the first part, in order to finally localize the robot itself. Also, the significant parallelics, that parallelic says that what is the differences between the apparent position of the object, that also need to have good distribution. We formally can call it parallax in image processing techniques. So in addition to those three, these three that we discussed here, we have I think 3 more. One is a local map in exploration, where optimization is focused, should be scalable. That if your map is like scalable based on the observation model that you have, especially this becomes important in drones when robot is flying. Not think about the only we are moving, everything is scaling a little bit. Initial estimation of the keyframe pose and location is very important also, because that's the initial construction that gives us opportunity to connect everything else to the initial estimation of the keyframe pose. And finally, the ability to find the fast global optimization of the poses that we have. So maybe our algorithm is work perfectly fine in local estimation of the differences, but globally destroys everything. That's not good. That these are the features of the bundle adjustment that can work based on the monocular camera, basically. So now specifically, if you want to talk about the orb and characteristics of the orb, we say it is feature-based monocular SLAM. And nowadays we have different also ones, but the original one that I'm talking about, the original first appearance of the ORB-SLAM. So feature-based monocular SLAM system that operates in real time. It covers all the SLAM tasks of the tracking, mapping, localization, and loop closing. We discussed this all together, separate sections, separate courses of this semester, tracking, how mapping is working, how localization can be extracted from those. It solves all of them, that we can call it is SLAM, not only localization. It uses ORB features that today we've seen how they are working. That is that most important reason is the being real-time performance. Without GPU, it can be performed, but of course, you can check it out if we have algorithms or implementation for GPU too, then it would be much faster to do that. As I know, ORB-SLAM is not compatible with GPUs yet. If you can do that, that would be great, but don't think that's easy, because if you look at the code, the things that I'm explaining today is tremendous amount of code over there for implementation. So, and of course, good invariance for changes of the viewpoint because of the rotation, the ORB-SLAM characteristics. It is real-timely operating in large environment and uses Covisibility graph that I gave you the idea what is it. That is tracking and mapping on the Covisibility graph for independent global map. And also, in addition to that, we have the real-time loop closing based approach that is optimization of the pose graph and called essential graph. So there is a technique that tries to improve the pose graph by essential graph. So I know lots of information, so all of these we studied today, and ORB-SLAM brings to connect all together. So to understand it, no way we needed to know about pose graph, ORB features, and all the bundle adjustment. Like here, we have real camera, relocalization as bundle adjustment that is that tries to recovery from tracking of the failure. There are some techniques that we will see in general projection of the how it looks like that tries to recover from the failure with significant invariance viewpoint illumination. Then we have survival of the fittest approach in it that as I mentioned, it has the keyframe selection as features of bundle adjustment, and the ORB-SLAM main design idea is to use same features in 3D in three different parallel threads, that is like tracking, local mapping, and loop closing. So they implement in general proposed technique. There are 3 threads, you know, threads, different codes of lines that can run at the same time together in CPU. So one is in charge to do the tracking task, one is constructing the map, including like pose graph and everything, and last one is in charge of the detecting the loop closings. You see that how important it is. It's also independent parallel thread in order to help the tracking and local mapping of the SLAM technique that we have. I don't know why this is blur, but here is okay, but there we have blur. So I take the picture from camera, the original paper. Here is fine. Anyway, let me generally explain. We have tracking part, 1 thread. We have localizing and map construction, and loop closing part, as you can see. Now, if you look at the details, we almost discussed all the details. For example, first, for frame is coming, frame of the camera, we are extracting the orbs at the beginning stage of the tracking. Then we are doing the pose estimation from local frame there, and then tracking local map based on those orb features, and new frame comes, and the new decisions based on these features, based on the orb features that we have as keyframe comes. So we are actually, it is generating new frame that is keyframe of these orb features. Then it goes to the local mapping as kind of it is working at tracking and filtering as initial frame. Then different techniques on the local mapping that we discussed, like for example, keyframe insertion, the recent map point cooling. I will explain now what it is. The new points creation, local bundle adjustment, and the local keyframe cooling. That this is like the I have it here. Yeah. This is retaining only high quality points. That is like kind of outlier detection, a technique. Of course, if we want to discuss exactly how it is in detail, you should have a look in the paper itself. So for the loop closing, they propose a technique that in this technique they are calculating the symmetry that is like applying some transformation constraints that tries to detect the loop closing between the features, the co-visibility graph that they constructed. So with some constraints based on the symmetry technique. Then you can see that what is in the map for ORB-SLAM. We have mapping points, we have keyframes, we have co-visibility graph, and we have a spanning tree. That this is spanning tree is like kind of brief version of the co-visibility graph that is for creating minimal number of edges to make it also much more lightweight and online. That again is like applying some like when this co-visibility graph grows, tries to extract the important elements of those co-visibility graph and try to use it in whole scenario that is happening. And lastly, in addition to those all elements that we have visual vocabulary and the recognition of the visual vocabulary datasets. That says, okay, not only doing all those efforts is enough, but also we can, with pre-calculated data, we can create visual vocabulary of the image frames that instead of like it's better to, if my camera sees this environment, right? Instead of orbs, if I can say that's chair, based on that co-visibility graph, chair, human, computer, it is nicer, right? If I can do that. So the idea comes from there, based on those orbs, graphs, and pre-trained, prepared the visual vocabulary data set, then even tries to make it in higher level of the representation of the environment. So that what we have here, you can see the examples over there that like the camera, this is the camera trajectory and the camera poses that sees some features in the inside and just example from A to B, C, D. Then in ORB-SLAM co-visibility graph specifically, each node is keyframe, and an edge between two keyframes exists only. We have common observation or same point observation of the point at least 15. It means that like frame A, frame B, so must be they are keyframe, both of these. If the differences between A and B at time t and t+1, there are some features that seeing and minimum 15 number of those features can be visible. Then the rule is like this is keyframe. So in constructing co-visibility graph of the ORB-SLAM. So because we discussed in general co-visibility graph, but you can see how the edges and nodes are defined. Then word of place, I already explained. We are it's training image features as words to perform loop detection and relocalization of the loop closing problem specifically, because this part is mostly focused on the closing the loop by keywords, because if you have words instead of features, it's easier to compare, quickly find the idea, chair, this should be loop closing. Chair, computer, laptop, this should be the same one that I've seen already. You see, for loop closing, this part is word recognition is very useful. I stated some points here. Visual words are just discretization of the descriptor space known as visual vocabulary. and the vocabulary are created are mostly offline, because okay, we can say that we can one time do it, then use it. No need to do it in online. But of course, you may think, okay, if you do it online, it's better. Apply some learning technique to do that. Yeah, it could be. If the image that we are doing that in offline way are enough, it can be good, and the performance will be nice over there. It should be fine. And it builds incrementally a database of what the features that we are seeing ORB-SLAM, and puts, like, you can consider, writes a sentence at each frame, right? Okay, I'm seeing these moves, and I'm seeing these, then matching in future. If I'm seeing the same things, then it will be working efficiently by querying that data set of the, for example, word vocabularies in each thing. What we have the versions, the 3 common versions. We discussed the first one. The 2 is trying also improve that one. The 3 is trying to improve that one, make it a little bit more complex, but general concept is same, not too much different. You can see the Monocular implementation. Also, it is ROS integrated. I put the GitHub link. You can download, install, and check it out for SLAM. And ORB-SLAM number 2, ORB-SLAM number 3, I shared the code with you over there. That you can see that second version. First version we mostly discussed with Monocular. Second version says, okay, not only cover the Monocular, we want to also use stereo camera, RGBD camera. So the proposed technique generalized to also be able to use on this, because this one has some problems. It's not working perfectly fine and is not adaptable. But this one, you can just take the code and change it to use with RGBD, for example. And lastly, third one, it is very important to say that it tries to use the visual inertial and the multi-map concepts. It means that, okay, we say we have camera and camera is moving, but we have IMU2 mostly in our robots. Why don't use it? We have momentum of movement, how fast the camera is moving. Why we don't use it? Why we are throwing out? In bundle adjustment, we saw, okay, that's very difficult to find the 60 OF of the camera where it is. So we can use that. How much is rotating? We can use that information. Then in ORB-SLAM 3, they added some elements to integrate it with this technique over there, simply. Not simply, but I mean the idea simply. So you can see the latest paper publication, ORB-SLAM 3, download it, study it. You will see the same things, more in details, more accurate formulation and equations. I have an example that works on the benchmark. So you can see that this is the orb feature extractions and map construction of the ORB-SLAM, that the camera is on the car is moving. You see the orb features that are moving toward, and they are in different frames, accurately can be detected. All the procedure that we discussed now is running in background in order to construct this map. Loop closing happened there, detecting the same features. For example, tree, car, tree, with word vocabulary that there were. Another loop closing happened. At the beginning was error, then quickly adjusted. You see there were errors like there, and after loop closing, it detected and constructed and improved the whole pose graph. And you can see that goes, if these same features is not seeing, and loop closing after detecting, after a while struggling, sees the same one, and you can see 3D constructed map, And the ground truth, very similar. This is the exact one, and that is the map that it is there. But now, let's see another video based on the RGBD camera. This is ORB-SLAM number 2 that uses the RGBD camera. You can see a person takes the camera, and you can see the pose of what we were talking as bundle adjustment, and you can see the position of the pose of the camera on the 3D environment. You can download it and do it on camera yourself. Try it. You can see in 3D space, not only for big campus areas with the ORB detected features. We can extract the environment like that, and again trying on this one. This result is for a stereo camera. Previous one was for monocular camera. You can see the data is more accurate and stable at the beginning stage. In highway, because we have depths, again more stable. Another example with RGBD, rotating, like there is a table and some computers, like similar to this part. The guy is moving the camera, and you can see that almost very accurate. And now trying to, after constructed map, only running localization to see with running the same trajectory to see how accurate it is. Almost, you can see this green point, almost accurate with the same path and the location. But here there are some errors. It went inside too much. And 3D construction of the map, because we have RGBD, then we have the depths. We can just plot the depths on the 3D mesh. Then we have this. It has the features. If you enable in the ORB-SLAM tree, you can do the same thing with output. And one more example. No, before that, let's have a look at the comparison tables of the recent SLAM algorithms on visual. So these are all different techniques that has been proposed for SLAM, but just a small part. There are much more. I know like 3 to 5 different also improved versions of SLAMs that I've seen recently. Just one also I reviewed myself. So for a journal paper. So here you can see different techniques like mono-SLAM, like PTAM, and comes to the ORB-SLAM here, ORB-SLAM number 3. That is latest one. You can see the if it's visual odometry or not. That is like, this is solving full SLAM problem, SLAM. This is like visual odometry. That is like localizing. Visually, camera is moving, and we want to localize, not construct the map and do all the other things. The types that you can see different. This one, ORB-SLAM 3 is SLAM. The pixels that they are used, you can see. For example, these are like fast. This is like ORB. This is another technique. And ORB, this one is ORB that we studied together because we were focusing on the latest one. Data association part. Here is descriptor. We now know what does it mean. I clarified for you. What we have as estimation, we have local bundle adjustment for ORB-SLAM. You can see different techniques. For example, this guy over here have been used ETF. Now you know. So this one over here used pose graph directly, purely, not local bundle adjustment. Then I move to this part. Over here you can see the features that we have. So for example, multi-mapping, if it's covering or not, monocular, stereo, monocular with IMU, is it is it covering or not? Fusion, fisheye lens camera, is it covering or not? And what is the accuracy? So you can see ORB-SLAM 3 has all of these features together in comparison to different ones. And the accuracy is excellent, as they claimed, and it is excellent. For the others, they've written good, good, very good. But this one is also excellent here. ORB-SLAM number 2. If you come, it's like same family. Then robustness, like fair or excellent, they compared, and finally the paper that you can go download and study it. So this gives us very clear image of the researcher studies that if you want to do SLAM, go work on this guy over here. But of course, I would go to the Google Scholar, see who cited this guy, and see what are the recent works and who tried to improve it recently. Because, for example, one of the improvements is like outlier detection with removing dynamicity of the environment. Like with detecting orbs, we are extracting all features. But if we say these are humans, that maybe they go away after some time, and we remove them as outlier and rely on more reliable objects, or detect the dynamicity of frames. Between frame A and B, something is moving. You are moving there. So you are going out, for example. Then I know that that's moving in the frame. That's not reliable feature as orbs. Then I cut anything that is moving in frames. Then those techniques are nowadays improvement of this guy over here. So we have one more example from the laboratory. You guys mostly have seen it from previous semester. One of the students did it in campus lab, the ORB-SLAM 3. You can see the output of the ORB-SLAM 3 in the campus with Gogoro project, the constructed map. Before Ugo came here, we were struggling with that one. Sun did it, one of the students on the line. You can see that loop closing problem happened there. And pretty accurate construction of the campus. And you can see that the location of where the Gogoro is based on monocular camera is still accurate, and those are all features over there that you can see, and very accurate output. And what we discussed today, we discussed the mapping without uncertainty first, then with uncertainty first. We understand the main concept. We introduced the post-graph optimization. We talked about the feature extractions techniques like SIFT, BRIFT, and ORB. Then we talked about the bundle adjustment technique and what is it we said that whole ORB-SLAM technique want to solve this. We talked about the visibility and covisibility graph general concept, and we talked about the general construction of the how ORB-SLAM is working. Of course, if you want to go in detail, you need to study more, and that's it for visual part of SLAM for today. Any question from anything? Yeah?
Do you think it's better to use a stable camera or RGB cameras?
You can use, yeah, can give,
will give the best result.
yeah, it will improve the accuracy at the beginning stage for you. And I told you, you can use it. It's okay.
I mean, what I'm saying is which one would be the preferred one? Like, you prefer to use stereo or RGB?
It depends on if you are a fan of Elon Musk.
Okay.
Yeah, if you're not fan of Elon Musk, it's like, yeah, for me, for me, it's like, for me, using more sensor information that is useful is better than give you more reliability. Yeah, because that's big project, expensive project, I would say it like that. But if you want to say, no, we are going to propose a technique that is generalizable and is not expensive, everybody can put a camera and do this job, then the camera is better. Yeah, depending on motivation. But for now, if you ask me, I would say which one is working better, use that one to do the job. Then later we can like replace the one that is not working better and try to improve. Any other question? So today's course I think is very useful for future careers also. I highly recommend to study the more details on the references that are given to you with the publications and papers. And I think this brings us to the end of this semester, because next week is the final exam date that you will have final exam, and you know the regulation. I already stated what are the requirements and what are the points that you have, the marks. Don't forget your project, and your project, as I told you, must have been stated in the Moodle so far, what you are going to do. Then next week exam, then later for the project I will give you as much as time as I can that I need to put in the system, but there is limitations, then I will cut it there, then try to don't miss the deadline. Any question? So thank you very much, good luck, hope you learned useful information from this class this semester. Good luck.